Hello everyone, greetings from VNR, JYOTHI Institute of Engineering and Technology. This is Manohar Reddy, Department of Cybersecurity, Data Science and AIDS. Today in this concept I am going to discuss about the concept of semaphores. So what is meant by semaphore and how the semaphore will be the solution for the process synchronization problem is we are going to discuss in this section. So a semaphore is a synchronization tool that does not require busy waiting. So semaphore is one of the synchronization tool to solve the process synchronization problem, and also we can call it as a semaphore is a integer variable which shows that does not require any busy waiting for another process. So the main aim of this semaphore solution, the main aim of this synchronization tool is to do not require busy waiting of another process. So the semaphore is an integer variable. The semaphore being an integer variable is assigned to initial value. The initial value denotes the number of processes. The initial value, the semaphore value, we can denote as S. We can denote it as a S, and the values either 0 or either 1. The values will be either 0 or either 1. The initial value denotes the number of processes that can simultaneously access the shared resource guarded by the semaphore. So this semaphore variable performs the operations in the critical section itself only, because the critical section allows each and every process to access their shared resources. So what are the operations that can be performed in the critical section and with the solution semaphore? So with the solution semaphore, the two operations, wait and signal operations, are performed in the critical section. So whenever the process entered into the critical section, it must perform one operation. After completing the shared resources access, it uses another operation. So here there are two types of operations performed, wait and signal, in the critical section. Similarly, the solution semaphore, there are two types of semaphores are there. One is binary semaphore and the second one is what? Counting semaphore. So the binary semaphores are nothing but they can only be either 0 or 1. And these binary semaphores are also known as mutex locks. So mutex are nothing but mutual exclusion locks. As the locks can provide mutual exclusion, they can be called as mutex locks. All the processes can share the same mutex semaphore that is initialized to 1. So when it is mutually excluded semaphore, then it is be initialized to 1. Then a process has to wait until the lock becomes 0. So when it mutex semaphore is 1, that must be unlocked, and when it becomes 0, until the lock it becomes 0. So until it gets the lock, it becomes 0. So a process has to wait until the lock becomes 0. So that means the process has to is in the ready position. After finishing the process into the critical section process, then other process has to wait until the lock becomes 0. So the exit, it has to move to the exit section. And next, second one is what? Counting semaphore. So binary semaphore applies both zeros and ones for a lock, and for a lock becomes 0. And counting semaphore, in this, whenever a process wants to use the resource, it must be entered into the critical section. Obviously, it checks if the number of remaining instance is more than 0. And is there any remaining instance or more than 0, the process has an instance variable, that is, the process has an instance available or not. Then the process can enter into the critical section. If the process has an instance available, the process can enter into the critical section. If the process instance is not available, then the process cannot be entered into the critical section, thereby it decreasing the value of counting semaphore by 1. So whenever the process can enter into the critical section, if no instance is available, then it will be increasing. If instance is available, then it can be decreasing by the counting semaphore by 1. So to increase the processes into the critical section, then instances must be decreasing one by one. If the no processes are available in the critical section, then the processes decreasing semaphores by 1. So when the space is free, then the critical section is available, then counting will be increasing. When the critical section is not available, then the counting may be decreasing semaphore 1 by 1. So after the process is over, with the use of the instance of the resource, it can leave the critical section, thereby adding 1 to the number of available instance of the resource. So initially first critical section is empty. Initially the critical section is empty, 0. That means no processes are there, instance are available, instance is available. So whenever the process entered into the critical section, then this instance is available and this is applied to the process. So automatically the counting semaphore will be decreasing. Automatically counting semaphore will be decreasing because the available instance is assigned to the process. So whenever the new process comes, always the available instance is assigning to the each and every process, so that it will be decreasing by 1 semaphore. So whenever it is free, then the counting semaphore will be increasing. After using the critical section, it leaves to the exit section, then it will be increasing, 1 by 1. So whenever the instance is available, then process is ready to use that resource, so the instance available are decreasing. Whenever the processes are utilizing the critical section, it moves to the exit section, then the available places are increasing, that is increasing by the semaphore +1, and the remaining instance of not available are decreasing. So the instances available and not available are depending upon the process entered into the critical section. So if no processes are there, then the instance is available and it will be increasing. If number of processes are increasing to utilizing the critical section, then the instances available are decreasing. So like the way counting semaphore works. So based on the process synchronization, we have a classical IPC problems are 3 types. Various classical IPC problems are including producer consumer problem, reader writer problem, and dining philosopher problem. These 3 problems are IPC problems, or you can say that process synchronization problems also. But to solve these all problems, we can use the semaphore concept. So semaphores, we can have the semaphores 2 types. One is binary semaphore and the second one is counting semaphore, right? So whenever to solve these types of problems, you must ensure to write the code on, you must ensure to write or avail the critical section operations. So you need to write the critical section process for all these type of problems. We'll see producer consumer problem, how it will be solved by the critical section problem, how it is solved by the semaphore concept. So here the producer consumer problem is a classical example of process synchronization. So it is one of the classical example of process synchronization. It describes the situation where 2 types of processes, producers and consumers, share a common limited size buffer or storage. So what they are doing, so how producer will produces and how consumer will consumes. So a producer creates or generates data and puts into the shared buffer. So this is the shared buffer. So here the producer is available here, and here consumer is available. So always producer wants to produce something and the consumer always wants to consume something, right? So they want to ensure that do not make shared buffer is to be empty, and shared buffer is do not empty and do not overflow. So the producer has to ensure that the shared buffer will not be overflow, and this consumer will make sure that do not make shared buffer has to be empty. So how they are taking this challenge? This challenge arises because both the producer and the consumer need to access the same buffer at the same time, and if they do not properly synchronize their actions, issue can occur. So if they are not cooperated, they are not coordinated to each other, then what will happen? Producer always producing something, consumer always consuming something, means there may be a data inconsistency process, right? So to avoid this type of process, to avoid this type of problem, the two processes can be cooperated to each other, So because of this only, we have to use this problem solution as a semaphore. So key problem in the producer consumer problems are, one is what? Buffer overflow. So buffer overflow. Second one is what? Buffer underflow. If the producer tries to add data when the buffer is full, there will be no space for the new data, so causing the producer to be blocked. So shared buffer is full, then no other buffer data is to be added, then automatically producer to be blocked. And second one is what? Buffer underflow. The consumer tries to consume data when the buffer is empty, it has nothing to consume, causing the consumer to be blocked. So if no data is there, then the consumer do not consuming anything, that leads to buffer underflow. And similarly, producer produces a lot of data into the shared buffer, so consumer will not doing anything, then automatically shared buffer is full and overflow together, that is buffer overflow. To solve this problem, found main challenge is to ensure that what? A producer does not add data to a full buffer. So the producer does not add data to full buffer. So if the shared buffer is full, our solution is what? To producer does not add data. So if shared buffer is full, producer does not want to add any data. If consumer does not remove data from an empty buffer, so if shared buffer is nil, that is no data available in the shared buffer, then consumer does not remove data. And multiple producers and consumers do not access the buffer simultaneously, that preventing race conditions. So, and we have to ensure that what? Multiple producers and consumers do not access the buffer simultaneously. They do not access same time. So one time for producer and one time for consumer. That like that we have to assign the time, or we have to assign the process. So to manage this, we use three semaphore concept. So we already said that what? Semaphore is a classical solution for the process synchronization, and it is a variable, contains zeros and ones as a binary semaphores, and counting semaphores as increasing and decreasing counting semaphores. So here the first three semaphores we are using. The first one is what? Mutex ensures mutual exclusion when accessing the buffer. So when you are trying to access the buffer from the producer point of view or from the consumer point of view, use this mutex for the both processes. And the second one is what? Full semaphore. It counts the number of filled slots in the buffer. And third one is what? Empty. It counts the number of empty slots in the buffer. So how we are going to initialize the semaphore? So mutex equals to 1. That means both processes are together cooperated. So binary semaphore for mutual exclusion applied. So two processes are together in the position. Then first full equals to 0. Initially no filled slots. That means in the shared buffer, no filled slots. So no filled slot, that is 0. And empty equal to buffer. Buffer size is what? N. That means buffer size is what? Empty. That means automatically if no filled slots are available, means buffer size is empty. So how we are doing? So producer performing the operations, produce an item, wait and empty. So if we check for empty slot, if any empty slot is there, yes, because we initialized no filled slot, right? So because of that, the check for empty slot, there you found that empty slot, then wait mutex, so enter into the critical section. So according to that mutex process, they are executing. One process is ready to enter into the critical section and other process is ready to waiting. After finishing that critical section, it must be exit, then other process can enter into the critical section. So for this, for producing, these two operations are performing. And now place item and buffer. So now we got empty slots, and we call producer. So we got empty slot, we got producer with the help of consumer, and now the producer is doing the operation. Producer is doing the operation signal of mutex. So exiting the critical section, signal of full, increasing the number of full slots. So they are filling the each and every slot. So this is the critical section. After entered into the critical section, they are filling all the available slots. Filling all the available slots, 1, 2, 3, all the available slots. After that, call the signal mutex operation, exiting the critical section. So from the critical section, it must be entered into the exit section. So while of true. Now the producer operation is over. Now consumer is ready to enter into the critical section because the signal of mutex is performed. That means the producer exited from the critical section. Now consumer is going to use that one. So wait of full, check for the filled slot. So already producer filled 3 slots, right? So now consumer is ready to enter into the critical section. Wait of full, check for filled slots. So 3 filled slots are available. Now wait of mutex entered into the critical section. So consumer entered into the critical section. So after entered into the critical section, it checks for filled slots. So already 3 filled slots are available. These are filled by the producer. So now signal of mutex operation, signal of empty. So increase the number of empty slots. So all these 3 filled slots can be used by the consumer, consumed by the consumer. So now all these 3 slots are consumed by the consumer. After consuming all these, shared buffer will become 0. Now signal of mutex exiting critical section. So the way the producer and consumer both are operated together by cooperating manner. If producer producing something, then consumer is ready to consume something, then both operations are performed at the same time, then deadlock will occur or data may be inconsistent, right? So because of this, the signal operation and wait operations, these two are semaphore operations. They can be performed for both producer and consumer problem. So here you can see the explanation of the problem. Empty ensures that producer does not overfill the buffer. So full ensures that consumer don't consume from the empty buffer. So consumer will not take anything from the empty buffer, and producer will not overflow the filled buffer. And mutex ensure mutual exclusion. So only one process accesses the buffer at a time. After giving the mutex for producer process as well as consumer process, then that mutex shares sharing their waiting and signal operations to each other. The producer consumer problem is the fundamental example of process synchronization in operating system using the semaphore and mutex. So here the producer don't overfill the buffer, consumer don't consume from empty buffer. Mutual exclusion is maintained when accessing the buffer. This approach prevents the risk conditions, data inconsistency and deadlocks, making it reliable solution for coordinating multiple processes. So like the way the process, if the two process, even you can see in the real time example also, if two persons are competitive to each other, if two persons are cooperative to each other, what will happen? The two persons are cooperative to each other to access anything, then they will discuss one by one. They will discuss about that one, and one person can go and use that one, and the other person can wait till the first person came, right? So that is in healthy competitive way. But if these two persons are not coordinated, then what will happen? The two persons are trying to access the same item at the same time, then automatically the item may be lost or item may be damaged, right? So to make the data consistency, to make the data availability, the two or more processes are together to cooperated to each other, So I hope all of you understand about this topic. If you want to get the multiple content or more content on the process synchronization semaphore process, you can use these following links. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.